Okay, guys, I just want to do a quick review, but we've covered this term thus far for our wave topics, and then finish off our third inquiry question. Okay, so let's just gloss over a couple of things. We can probably zoom in a bit here. Okay. Now, remember, we've talked about two major types of waves. We got mechanical, we got electromagnetic. Electromagnetic travel at the speed of light. Mechanical require a medium and have some kind of finite speed determined by that medium. Mechanicals can be broken down into transverse and longitudinal, whereas electromagnetic waves are just transverse waves. Okay. We spoke about this idea about frequency and wavelength being inversely proportional. So you can see here, as the wavelength increases from right to left, that frequency also decreases. But if you go from a larger wavelength to a smaller wavelength, you can see that as the wavelength is decreasing, the frequency that's occurring over some set finite time in seconds, over 1 second, is increasing. So they're inversely related. As one increases, the other one decreases. Okay, we also talked about the idea of conservation energy. We briefly talked about this idea that energy cannot be created nor destroyed. And what happens is whenever you create some kind of mechanical wave, that mechanical wave doesn't keep the energy that you imparted to it all the way through. Some of it gets lost into the environment as sound, heat, even just going against the motion of the particles in the atmosphere takes some of that energy. So therefore, you can never get 100% of that initial energy that you added to that wave. This is not the case with electromagnetic waves because they just do their own thing. They do slow down somewhat when they go into like mediums, which you're going to cover up you're going to cover in inquiry question number 4. But in general, they just go on forever unless they strike something and get absorbed. So if I shot a beam of a laser beam into the distance, now some of the photons that made that beam will fly forever into infinity, into some kind of distance far, far away until it hits some other planet or some alien or whatever. Okay. Okay, very good. That's all right. Okay. Do I have a diagram here? No, we don't. Okay. So with longitudinal wave and transverse waves, they both are kind of the same thing, except in a transverse wave, we can model that as a water wave or some kind of, fabric being shaken or a whip or something. What happens is the medium, let's say it was the whip, that would actually oscillate up and downwards. So the particles in that medium will move up and downwards, and the energy would go forward. So they say that they go perpendicular to the medium. The motion of the wave is perpendicular to the medium. Whereas with a transverse wave, the particles oscillate back and forth. And what happens is they actually oscillate in the direction of the wave, right? So they're parallel to the wave. Now, in a transverse wave, the peak, the uppermost peak is called a trough, and the lowest most depth is called a trough. They got equivalent points in a longitudinal wave, with a compression being equivalent to the high point and the refraction being equivalent to the trough. Okay. Okay, I think these are probably good to look at. So let's look at these. Okay, so here are the two waves. Hopefully you can see it. It's not patchy in your computer. But okay, so see what happens to the waves. Nice and big wavelengths. We increase the frequency. Okay, those wavelengths are decreasing correspondingly. Boom, boom. Okay. So let's continue on. Okay, let's move on to our second inquiry question. Okay, with our second inquiry question, we talked about, we were getting to the point that we were saying that waves can be treated as rays or just straight lines. And the reason why we do that, it just simplifies other things that we want to examine. So we've gone from talking about mechanical waves and transverse and how they're transverse and longitudinal wave, to just seeing what they do when they hit things or when they, move through things. So well, this is quite a good diagram because it's elaborating on how, at a really far distance away, most sound waves, because sound waves do move in a three-dimensional, which is, most waves are generated in concentric circles or in circular patterns like so. And what happens at some real distance far away, that circle is so big that it's just one straight line. And that's what we can model those lines just going through, going parallel through those wave fronts, right? Wave fronts are the orange or the spherical ones, or the ones that are parallel to the rays, and the rays are the ones that are blue, that are going perpendicular to the wave fronts. Okay, and we use them to explain a lot of things. So we talked about the law of reflection. So this idea that if you have some kind of imaginary reference point, the normal, and a light hits the surface at some angle to the normal, it should bounce off at the same angle as an incident. So if you were to measure the angle between the incident to the reflection, it would be just twice the incident angle. I mean, it's quite intuitive, right? As light hits a surface, the angle that it hits it, it's the same angle that it bounced off it, right? If it didn't work that way, we wouldn't be able to see ourselves in mirrors. Okay. We talked about refraction. I don't think I have a diagram here for refraction. So let me get the booklet out so we can look at that. Okay, here we go. Guys, remember these booklets? Don't lose these booklets. These are really important booklets for you guys to revise your notes. Go over those questions again, make sure you understand them, because they're going to be very invaluable to you. I forgot to talk about these graphs. These graphs, remember, you got two graphs. You got a vertical displacement versus horizontal displacement. And with these ones, you can get the amplitude of something. You can also get the wavelength. Sorry, you get the amplitude of a wave. You also can get the wavelength of a wave. And the wavelength is the distance from one crest to the next, or from one particular point that repeats itself again in another phase. And these other ones are a vertical axis versus time one. And this one gives you the period, or the frequency, right? The amount of waves that occur in 1 second is equal to the frequency. So it's important that you know how to extract information from these diagrams. This equation, I'm going to go over this equation, very important. Remember, that's kind of the only equation we'll be talking about. Today, we're going to encounter another one, which is going to be a little bit more difficult. But remember, the speed of that wave, whether it be an electromagnetic wave or it might be a mechanical wave, is equal to the frequency multiplied by the wavelength of that. And that makes sense if you look at the bottom one. Wavelength, the amount of time it takes a wave to do one wavelength is equal to the speed. It's almost like that thing, that equation for speed that you covered in year 10. Distance divided by time is equal to speed. It's the same business here, right? The speed of the wave is equal to the frequency multiplied by its wavelength. Yeah, I haven't included that variable here, so I'll edit that now. That's interesting. V is equal to speed in meters per second. Okay, and that's lowercase v. Sine waves, well, we use sine waves to communicate, we use it as a model to explain transverse waves, okay? We don't need to talk about radians yet. We'll talk about radians in year 11, sorry, year 12. Yes, we talked about displacement and position versus time graph. Guys, don't lose these booklets, they're going to be very important. So let's look at refraction. Okay, so remember the idea was, if something is coming, if a light is hitting is coming from a less dense medium into a more dense medium, it bends towards the normal, right? But if it's going from a dense medium into a less dense medium, it bends away from the normal, right? Refraction. The reason why refraction happens, we spoke about how these waves, as they enter, you can see they start bending. So if you see this wave from A to B here, right? That wave, that's not really how you define it. You can see part of it has actually entered the denser medium first and the other is still waiting. So you can see this starts to slow down. Everything else slowly gets displaced towards the normal, right? Okay. And that's what I wanted to talk about, sorry. Let's go back there. Okay, so we talked about refraction. We talked about the law of reflection. We talked a little bit about diffraction. Remember, diffraction has to do with how much a wave, I guess, warps or alters as it hits different surfaces. So like these diagrams, if you got, the condition was, if the wavelength is larger than the width or whatever is obstructing it, if it's way larger than that, then the diffraction is going to be great. If the width is very small compared to the wavelength, then the diffraction is going to be great. But if you've got a humongous opening, like a, I don't know, let's say a big, you know, grand entrance to some kind of hole, and you yield at that hole, that big entrance, then that sound that you created won't diffract that much. But if you did it through some kind of little, I don't know, say 1 centimeter hole, then that sound would diffract as it goes in there, and you'll get more bend in the waves that you create. Because what happens is, as that wave hits the corner of that that barrier or that opening, what happens is it's almost like that wave has been destroyed and you get new waves that are being created from those different points, and that's why you get these diffractions. Okay, excellent. Okay, superposition. Well, that was kind of the heart of our out of our depth study. So it's this idea that when two or more waves interact with each other, it might be this wave here and that little wave there. When they mix together, you get some other weird wave that's formed, right? They add together, right? So you can see, if you add 1 unit from this to that, you are going to get this weird hump that happens here, but you're subtracting 1 unit of this side from here, so you get this really weird decrease there. So you can see that's what happens here. Or the most blunt example is this, where you have two waves coming at each other, equal amplitude. When they get to one point where they meet, nothing happens, but they continue on. All right, it's not like they mix forever. They just mix temporarily as they pass each other, as they pass by each other. And the other one is this, where they have same amplitude, same direction. They constructively interfere, and they go on with their merry ways. Okay, destructive interfere would be the other way around, where it ends up downwards. Okay, we talked about standing waves. So when this builds on constructive and destructive interference. So what happens is when you strike, the one that we did, we strike a rope at a certain frequency. And what happens is as that rope bounced back and forth and came back, it constructively interfered in certain places. And we called those places antinodes. And it destructively interfered in places where there was no displacement that occurred, and we called those the nodes. And what happens is that was related to the frequency that you strike that that rope. And if you increase that frequency, well, then you'd have more antinodes that were forming. So we called them standing waves. Now, standing waves, after our investigation, our depth study, we found out that standing waves not only happen on rope, but they also happen in sound. So with that was the pipes. The pipes created certain standing waves that depended on the length of the pipe. So the longer the pipe, the larger the standing wave, and the larger the standing wave meant that it had a lower frequency, it had a lower pitch, and so that's where we went with standing waves. Now, resonance was an interesting one. So resonance dealt with how objects have properties relating to them that allow them to vibrate more easily at certain frequencies. So when you guys were doing that investigation, when you were striking the closed, the pipes that were in water, that were effectively closed pipes, and you strike them you strike a tuning fork, and you brought the tuning fork on top of the closed pipe. What happened was there was certain lengths that the pipe would resonate, right? So that was the property of that material, of that system or pipe that you were changing in order for it to resonate. Now, this is not limited to pipes and strings. So I know with a string, depending on its length, you can get it to resonate at a particular frequency, right? The smaller the string, the higher the frequency. The longer the string, again, the lower the frequency. With we did one in our first investigation that we did, the swing. That was another thing that had resonance, right? It could only, the pendulum roughly, depending on the length of the string of the pendulum, it could only have a period of a particular time, and it was dictated by that length of the string. And that is also an example of resonance. It moves back and forth only at that frequency. But here, the definition's a bit more, I guess, abstract here. It says here, objects and mediums have preferred frequencies that they prefer to oscillate at. Okay, that's what we've been talking about. It is easy for them to develop standing wave patterns of oscillations at these frequencies. When you add more energy, / force input to an object or medium, the amplitude of the oscillation gets larger. It is said to experience resonance. So I guess going back to the swing example or the pendulum, if you are on a swing and somebody's pushing you on the swing and it takes about 2 seconds to go from one phase, from one side to the next, from one side back down again. Have a look at this, we've got a nice picture here. You know, you go up and back down. It takes you, was I saying 2 seconds? Say it took 2 seconds. So 1 second this way, 1 second back. So it took 2 seconds to complete one period. So what happens is if you're pushing that kid every second, so you're running up to him, you're pushing him up, pushing her up, and then going back where she was and then pushing her again, you're not adding more energy to the system. You're effectively destroying that. So when you're pushing that kid at the right frequency, then you can actually get them to go higher and higher and higher, right? If you do it the other way around, then you start to slow them down. You take away from the resonant frequency. Okay, let's continue on. Okay, this was us for the sound wave topic, right? Which was this one here, waves and thermodynamics, sound waves topic. Okay, we talked about, we were building on this idea about sound. It's almost like we talked about, certain properties of waves. We talked about its features, and now we've just moved on to sound. The next inquiry question next week that we're going to talk about is about light, so electromagnetic waves. But we talked about this a fair bit, which was sound is given by the decibel scale, and we haven't spoken about the nature of the decibel scale. But what happens, you can see a pattern here, is that they go up by 10. And the reason why it goes up by 10 is that any minuscule sound between 0 to 10, it's almost indetectable by us. And we actually did an investigation here where we noticed that we're limited in how much energy we can generate with our voice to about 50 decibel at the best screen. And we're also limited in what frequencies we can reach with our voice box, so we can get a maximum of, what's that, 7,000 hertz. Okay. So yeah. Okay, how does sound propagate through a medium? So that was in the cover of a book. So it's this idea that we've got an atmosphere, as we have some kind of energy that's added to the environment. Here we've got a membrane of a speaker. As that oscillates forward and back, that pushes the particles and then pulls them back in. As that happens, and it happens at a certain rate, at a certain frequency, then you get that frequency propagating through the air particles in space, the air particles on Earth. Okay, if sound travels faster in a denser medium, why would sound travel faster in hot air, which would be less dense, all right? So yeah, hot air floats, right? So we talked about that having to do with the amount of extra kinetic energy that the particles have, and how they almost help you in getting your voice across, that particular situation. Okay, yeah, this had to do with units. And the reason why I had the units there was to build to this idea of the inverse square law. So it was this idea that if you had some kind of source, say that source was your voice, you're yelling at somebody, and say that person is, say 100 meters away, okay, maybe 10 meters away. The intensity of that sound that they would hear is given by how much dots you can see at this particular area, all right? So say that's how that indicated, say the density of the coloring of this particular area had to deal with the intensity of the sound that person heard. As that person, say, moved to, let's say they went to 50 meters away, that intensity of the sound would have decreased, right? And it happens in a three-dimensional way. We use the inverse law to explain that. So it's this idea that whatever sound you have from the original source decreases as it moves away, because it's got to cover more area to impart that energy that it was carrying with itself. And it happens to be that the intensity decreases by the inverse square. So at, say 1 unit of distance away, it's equal to, whatever value you got there. At 2 units away, it's a quarter of the sound, because 2 squared is 4. So 1 over 2 squared is 1/4. So it's 1/4 of the strength. At 3 times the distance, right? 3 squared is 9. So we get 1/9. And you can actually see these areas like actually show up. So one area here, your 2 distances away, you have 4 areas that you've got to cover with the same amount of noise that you created or light that you created. 3 distances away, it's about 9 square areas that you've got to cover. And it's related by the inverse square law. Let's have a look at that. Our books. Here we go. So it was this equation here. And we noticed that the inverse square looks like this, the graph. We did a graphing exercise like that. We've got another diagram there to illustrate that idea of the inverse square law. Okay. Okay. Didn't get to do the resonant activity, sorry. Okay, derive the frequency of a standing wave. Okay, yeah, we talked about the harmonics. So we went back to strings, and we were talking about we know that we can create standing waves, and we know that they're made out of antinodes and nodes. But we started talking about this idea that each one of those antinodes, because the frequency has changed, you have a different frequency, and that frequency tends to be a multiple of the fundamental. So fundamental is just half a wavelength. The first harmonic, we use harmonic, is much easier. First harmonic is just half a wavelength. Second harmonic is 1 wavelength. Third harmonic, you get 1.5 wavelengths. So we started talking about that, and the condition was that the amount of wavelengths present, the amount of wavelength present in a string of a particular value length was equal to this factor, which was 2 times the length divided by the harmonic is going to give you the wavelength and how it relates to the length of the pipe. The one that we derived was this. So it was this idea that the frequency of a particular harmonic experiencing some kind of length of a string here is given by this expression. So the speed of the wave divided by twice the length is going to give us the frequency. And that's what these harmonics had to do with. So remember, these harmonics, what happens is, yes, if you had a string and you moved it, faster and faster, you would get all these different antinodes happening there. And that's fine. But in general, how that applies to like real life is that as you pluck your string, you usually get a fundamental or a first harmonic happening. And what happens is, you don't get the pure tone. You actually get all these other tones appearing over it. So this doesn't look like a perfect half a wave. It actually looks like this really weird modulated string that is trying to do a first harmonic. And we call that overtones. All these are overtones, and they just give the sound a richer, I guess, a richer sound. The string a richer sound, and gives it a certain flavor to what sound it makes. Okay, now with our pipes, we weren't really calculating harmonics in the pipes. So with this one, you could change the harmonic by plucking the string faster. If you plucked it fast enough at a certain frequency, then you will get some of these different harmonics, and you might change the pitch slightly or the frequency slightly of the guitar string or the string itself. But with the pipe, the only way that you could get more harmonics occurring or overtones was by actually speeding up the air pressure that's going through the pipe. We never got to that. We were just looking at the fundamental frequency occurring in that pipe. Okay, very good. Okay, and this is where we're getting up to today. This is where we're starting today. Okay, we derived that. Okay, good. We haven't got that here. That's all right. Okay, now this is the speed of a wave on a string. That's what this is. So speed of the wave on the string, you got to consider the length of the string, the mass of the string, of the length of the string. So not the mass in the spool, but the mass of that particular string. And what happens is that gives you a special value, m divided by L. We usually use another variable, but we just leave it there so we can see how all these variables relate. And we call it the mass per unit length value. Now, yes, we're trying to figure out the speed of the wave, but you also have to consider the tension that the speed of the wave on the string. You also have to consider the tension experienced on that string. Okay, so what happens is, I mean, you know, if you get a rubber band and you stretch it out and you start plucking it, you'll hear like a you know, it's got like a sort of noise, you know, it starts, you know, like a bouncing noise. And as you stretch that rubber band, that sound, you know, increases in frequency. You know, you start hearing a sharper, a sharper, higher pitched sound. And you can, you know, move that back and forth, stretch it and decrease it. You know, you start hearing this sound. And what happens is you can see that variable relates, right? Tension. The other thing that you could do, I guess, is get different girth size rubber bands and see how that affects the speed of the wave. And, you know, because an increase in speed is going to, you know, definitely affect the sound, right? Frequency, increase in speed, you know, an increase in frequency. Okay, so they have an example problem here. Let's go over this example problem. And I might actually get my, I'm scared the camera won't work. So I might. Okay, sorry guys, I'm gonna have to buy a faster laptop or something, but you're just gonna have to bear with me and just kind of go with the flow here. And we'll work through these together. I mean, the solution's there, but I guess talking it through sometimes shows, I guess, a bit better intuition. All right, so here we've got an example problem that relates to this equation, right? So it says the lowest E string on a guitar has a frequency of 82.4 hertz. Okay, so you can see we're given some kind of value that doesn't relate there. We've got a frequency, okay? But we do have an equation for frequency of a string, right? So that can come in handy. If the guitar string has a vibrational length of 640 millimeters or 0.64 meters, remember you have to convert those units. Half of the work of questions is converting those units back into SI units, right? So 0.64 meters. At what speed do waves travel along its length? Okay, we got a frequency value and we got a length value. Okay, so right, it looks like we're not going to need this expression. We have frequency. We've got a length of string. Frequency, length of string, speed. Awesome, we can use this expression. We're assuming it's going to be a fundamental harmonic, which is 1, and 2 is a constant. So that's exactly what they've used here, right? So what they've actually done is, rather than using this expression and rearranging this around, divided by L, twice the frequency, twice the frequency times the length of the string divided, rather than using that, they've decided to solve for the value of the wavelength by using your standard wave equation. Sorry, by using the wavelength to length relationship. So they were saying, because there is you know, we're assuming a fundamental, we're assuming a fundamental frequency, right, divided by 1. We're saying that the wavelength, a wavelength would have to be equal to twice the length, right? Twice the length. If you had you know, 2 length size, then you get 1 complete wavelength for the fundamental frequency. But we don't get that, right? So we have to kind of, you know, explain it that way, which is the best way that we do it. It's still valid. We're not increasing the length of the string, which is explaining how the wavelength is measured with respect to the length of the string. So if you scroll back down here, that's what they're saying here. Wavelength is equal to twice the length of the string, because it's 0.64 meters. 2 times 0.64 meters gives us 1.28 meters. So that's the effective length of the wave. Now we can solve for the speed. So we know that the frequency is 82.4. 82.4 times 1.28 gives us a speed of 105 meters per second, which is this value here. That's the speed of the length. And it goes here. The low E string on the average guitar has a mass per unit length of 6.8 times 10 to the power minus 3 kilograms per meter. So for every meter, every meter has that 6.8 times 10 to the power negative 3 kilograms, which is, what's that, 0.0068 kilograms, right? What's that, 60, let's have a look at that. Yeah, so it was 6.8 grams. What is the tension in the stretch guitar string? So we got this value, we got the mass, we got the length, we just got to solve for tension. Okay, so we've got to do a little bit of algebra. So what happens is, if we take the square of the speed and take the square on this side, that means we get rid of the square root. So we end up with some middle position. So what I do now, once I got rid of this square root, I can multiply m divided by L on this side and multiply m divided by L on that side, and I end up with this expression here. So now I could just substitute in my values and solve for my tension. So don't forget your squared, because your speed has become squared. So 105 squared times 6.8 times 10 to the power minus 3. All right, yeah, so that's the unit per length value, times that, which is this value here, mass divided by length, gives us 75 newtons. Okay, let's move on. Okay, beats. This is an interesting concept. So we've spent a lot of time talking about how when you have waves of different amplitudes and different frequencies come and interact with each other, they destructively interfere and constructively interfere and create these weird, like, Frankensteins of waves. Beats is a bit different. What Beats considers is, you got waves of the same amplitude but different frequency, and what happens is, when they superimpose, they create these weird waves where, yes, you have your own little, like, you know, frequencies that are occurring in that wave, but there's also an overarching frequency that's created between, you know, it's almost like you got another crest here, you got one crest here, and you got another crest there, that creates a sound in itself. That will be a beat. That would be another beat. They'll create. It's almost like you're creating sound out of two sounds, and we can actually demonstrate this. Let's demonstrate this now. Call them beat frequencies. Okay. Right. Okay. Now what I'll demonstrate is with beats. It says here that the frequency, the amount of oscillations that you'll hear in over 1 second is equal to the difference between the two waves, right? Between the two frequencies. So say you got one that's equal, hold on, and this symbol here, that means that we're talking about the absolute value of something. So that's what you got there. So sometimes you might get a negative number. So disregard that negative number. It's always positive. It's the absolute value. So let's have an example. Okay. So say we wanted to get, say you wanted to get a beat of 1. So that means you want a frequency of 1. Okay, so normally this is how the 500 would sound. Hold on, let me see if this is working. Okay, try that now. Okay, hopefully if it works. If not, comment in on Classroom so I can do it again. Okay, normally 500 sounds like this. Whoops, no, not like that. Okay, 500 sounds like this. And 501 sounds like this. It's almost the same, right? But they are different frequencies. So what happens is, if you have a difference of 1 between them, you start hearing something different between them. You can hear that up and down oscillation. Right? That is the beat that you're hearing. There's a big difference from this. And that is just a constant tone. This is the beat. Okay. Now what I want to show you is that you will get 1 beat in 1 second. So you have a frequency of 1 second. 501 minus 500 is going to give you 1. So it's saying that you'll get a frequency of 1 as per the expression in your books. Yeah, right? 501 minus 500 is going to give you 1. So let's check that now. Okay. We said that. So let me just kind of get into it. All right, that was a bit of a delay. Yeah, all right, nearly got it there. All right, about 1 second. So it should, you know, if you were more on top of it, you could actually get the 1 second. But you can see you do have that beat. You have that frequency of 1 second created by that beat. Let's do one more. 2. So that means we'll have 2 wavelengths that occur in 1 second with this beat. Let's see if we can get. Better. Well, that's beat. It's the overarching frequency that results from superimposing two frequencies, and it just happens to be that the new frequency created, the beat frequency, is equal to their difference. Right? Okay, here we've got an example question. A musical instrument is played with a frequency of 359 hertz. Another instrument is played at the same time with a frequency of 361 hertz. What is the frequency? Sorry, what is the beat frequency hertz? Nice and easy. 361 minus 359 has a difference of 2 hertz, right? And that is your beat frequency that you hear there. Okay, Doppler effect. Okay, let's have a look at Doppler effect. Okay. All right, the definition says this. Okay. When the source of a sound is moving closer to you, the sound wave becomes closer together. The source of the sound wave chases the wave. So the source of the sound wave chases the wave it is emitting. The wavelength decreases due to this. So it's like you had somebody standing still at a distance, and you were, driving towards them in a car, and you were just kind of playing some kind of frequency towards them, and that person is listening to you as you're approaching. What happens is, as you're coming towards that person, not only is the sound coming to them at the speed of sound, which is 340 meters per second, no, it's also coming at them at the speed of the car that you're traveling in. And because that happens, you're effectively chasing that compression wave that you've created, and as you're chasing that wave, you've gotten closer to it, and you've decreased the wavelength of that wave. And what happens is, if you decrease the wavelength of that wave, you have effectively increased its frequency. So that's why it's heard as a higher frequency. So this is a nice example to kind of illustrate that point. Okay. Okay. So here we got some objects traveling, I don't know, let's say 4%, I guess it's 4%, 6% the speed of sound. Okay, nothing much is happening there. They are moving. You can't really see any difference happening. That's okay. Say we speed them up to, say, 30%. 40% the speed of sound. Okay, all right. You can see as that object is moving, towards the right there, as it's moving, it's trying to catch up with those compression waves it's created. Around the compression waves are the lines. The black is the refraction. So you can see it's trying to catch up with those compression waves, and the wavelength effectively becomes shorter. And because that wavelength becomes shorter, its frequency is increased, or it's perceived to be increased, even though the object is still releasing it at that same rate. It's always the same rate. It's always releasing it at the same rate. But because the wavelength has decreased, it's given the illusion that frequency has increased. So we kind of hear it as a higher pitched sound. I mean, if you think of yourself on the road, and you hear an ambulance coming towards you, you can hear it at a certain, normal slow pitch. But then as it gets closer and closer to you, it starts to get higher and higher because it's coming towards you. It's increasing the rate. It's squishing those wavelengths together and increasing the pitch. But then as it gets past you, you can see those wavelengths actually get they get much larger to what they normally were. So that's the normal rate of the wavelength. That would be the actual frequency that you would hear off that ambulance. But as it's moving away from you, you can see they get longer and longer. So you hear it as a more low pitch sound. Okay, let's give this a go. So we'll drop this down to say that, and we can actually put a microphone to kind of illustrate the point. So let's have a look. So here we're going to hear actually we probably should do it at a normal rate. Okay. So this is our normal sound. What's that? Detected frequency 2. So every second there's 2. 1, 2, 1. Okay, hold on. All right. Yeah, so yeah, over 1 second, yeah. So let's prove that. 1, 2. Okay, hold on. Let's try again, okay. 1, 2. All right, it does have a frequency of 2. So let's see what happens as we move this over here. So that's the source of the frequency is 2. Let's see what's the detected frequency as it moves towards it. So we're going to travel at 40% speed of sound. Let's do that. Okay. 3.2. About 3.2. But what happens as you get closer to the actual object, you see you start getting back to its original source. It's almost you're like at the source. You're at the source, therefore you're very close to it. 2.2, sorry, 2.33. Okay, so continue on. And now what's happening? All right, you've dropped from the source it's 2. Now you're hearing 1.67 hertz. As it continues to move away from you, it gets slower and slower until you get that constant slowness, which is 1.43. That doesn't, remember, these don't increase once, like that's the most you're going to hear, unless it's sped up. If that object was speeding up, then that will continue to decrease. Otherwise, if it's moving at a constant speed towards you or away from you, it's always going to be a constant frequency. But if it's accelerating, then that frequency would change. So here you can see 3.3. That's the constant frequency, right? And you move to the back of it, again, it should be 1.33, 1.43. Okay. Anyways, that's the Doppler effect. Okay, yep, you perceive it as a loud or sorry, as a higher pitch or a lower pitch. Higher pitch when it's coming towards to you, and a lower pitch as it's moving away from you. Now, this is probably one of the most ugliest equations you're going to come come to recognize over this topic, and it's called the Doppler effect. It's just for sound, the Doppler effect equation for sound. And remember, the Doppler effect is that perception of a higher frequency when an object is moving towards you with some kind of fixed frequency, and it sounds like a lower frequency when it's moving away from you. Okay. Okay, and that's what's being expressed in this image. The truck's moving towards something. Those waves are looking quite smaller, therefore it's going to be a higher frequency, therefore it's going to be higher pitched. As it's moving away from you, those waves are going to be perceived as being further apart from each other, therefore the pitch that you hear should be lower, or should be perceived to be lower. Okay. So what you need to understand is what this is saying. So what it's saying is that you have some kind of frequency that's being emitted by a source. So that's a fire truck, a person, whatever it is that's creating the sound, that's creating the frequency. That's what that F stands for. The F with a prime on top of it, or it's like a comma, sorry, like apostrophe, call it F prime. That's the perceived frequency. That's the detected frequency by the observer. So that's the different frequency, right? So as the fire truck, which has some kind of frequency, approaches you, you hear it to be some kind of higher frequency. Or as the fire truck is moving away from you, receding from you, you can detect it as some kind of lower frequency, okay? Now, V subscript wave, that's always the same value, which is 340 meters per second. That's just the speed of sound in our atmosphere. That will always have to be the same unless you were dealing with some kind of problem that was talking about the atmosphere in some other planet. And then you have these plus or minus symbols, which we'll talk about in a second. The other variables that you have, or the other terms, are V source. Now, V source is the speed of the object. So it could be that fire truck, what speed that fire truck is moving at. And yes, the speed of the fire truck, and V observer. So that's the person. So just as you can have an example where the fire truck is coming towards you, you can also have an example where you're running towards the fire truck and the fire truck is moving towards you, and those speeds at. So you have to consider that and how that would affect the frequency. So these are the rules. So you've seen these plus or minuses in your quadratic equations. Here, what they mean is, depending on the scenario, it could be the observer moving or approaching the source, or it could be the observer minus moving away from the source, right? Now, the bottom one, it's the same thing. It could be the source moving to the observer. The plus is the source moving away from the observer. The minus is equal to the source approaching the observer. That's all you have to remember with those symbols. If you choose them in the right order, you won't have any problems. So remember, if the observer is moving towards the object, it's a plus. If the object is moving, if the person or the observer is moving towards the source, you include a plus. If that's not the case, if the case is the observer is moving away from the source, then you include the negative sign. Now, once you've done that part, you have to consider the bottom part, which is the source moving to the observer? If it is moving to the observer, you use the negative sign. If it's moving away, then you put the positive sign, okay? Now, what happens if the observer is stationary? Then you don't put this value at all. You just get rid of that. If the car or the object making the noise is not moving, then you don't put that term at all there either, okay? And that's how you use that expression. So let's have a look. Okay, here we got an example. It says, the siren from an approaching ambulance has a frequency of 800 hertz. Okay, pretty simple. The ambulance is traveling at 25 meters per second. Okay, so we know that it's moving. A car, which is the observer, is moving towards the approaching ambulance. So they're coming towards each other. What is the frequency that the sound is heard by the person inside the car? So let's have a look at that. So we know that the observer is approaching, so we're going to have a plus on the top, and we know that the source is approaching as well, so we're going to have a negative at the bottom, okay? That's what we got set up here, plus at the top and a negative at the bottom. Excellent. We know the frequency is 800. Good. We know V, which is V source, is 340, right? So those are the same. We have to add 15 meters per second of the car, and we have to subtract 25 meters per second of the ambulance. And then once we come up with that ratio, we multiply that by 800, and that's going to give us our new frequency. Okay, let's have another, we've got another example here. We'll walk through this example as well. Okay, a stationary observer hears a car horn as the car drives towards them. Okay, so here we've got somebody just standing still. The frequency of the car horn is 300 hertz. So it's 300 hertz, the car's moving towards him, and the car is moving at 20 meters per second. So let's have a look at what that's going to look like. So observer, 0. So it's just going to be 340 divided by 340, it's approaching, minus 340 minus the speed of the observer, which is 20 meters per second. So let's do that. Here we go. 300 multiplied by 340 divided by 340 minus 20. That gives us a frequency of 319 hertz. So you see that there's a 19 hertz difference in the frequency heard by the observer. It sounds a higher pitch. The observer hears a higher pitch car horn of frequency of 319 hertz. Okay, these questions, I'll get you guys to have a go at these questions. You shouldn't have a problem. A lot of the questions are just Doppler effect questions, just to test you guys understand how to use that equation. You know, choosing the right combinations of values. When is it a positive? When is it a negative? And then you've got a little bit of algebra here. I want you guys to start practicing your algebra. We'll go over this question next time we see each other next week. A frequency analyzer in a fixed, okay, again, okay, what's the plane's velocity? Okay, you're gonna have to do some rearranging of the Doppler equation. So you should be able to do all those. See how you go. We've got some stuff on strings and frequencies and harmonics, and we'll go over that. But yeah, just remember that. Rewind this video and have a look at these if you don't understand, and look at those examples.